and it's chi-square analysis. It looks like chi, but it's pronounced chi. And it's a way for us to make comparisons between multiple proportions. So you're probably thinking, well, you know, we already did a chapter on proportions, a 1 proportion z-test, 2 proportion z-test, but this is for 2 or more. So it can really allow us to expand into taking groups of proportions and seeing if they're either all equal to each other or equal to a standard, or if there's an interaction in the categorical variables that produce these proportions. So we've actually got 3 different kinds of chi-square tests. We started today with the chi-square goodness of fit test, which is here under A. And it's like, do Skittles end up, the colors of Skittles end up in the same proportions that the manufacturers claim that they do? We're going to do the same thing to illustrate that, only we're going to do M&Ms. So color would be the overall categorical variable, which would then break down into red and green and blue or whatever colors happen to be there. The other 2 are actually where we will interact more than one categorical variable, like gender versus political party affiliation, you know, that sort of thing. And so we're going to have 2 different kinds of tests that are really pretty similar, at least in how they're executed. We'll have a test of independence, and I'll need for you to add in a test of homogeneity. In fact, these notes are a little bit, they need some revamping, so write a few things in, maybe scratch a few things off. So the chi-square statistic is the next thing to look at, and it's going to be very different from a normal distribution. Normal distributions, t-curves, z-curves, those sorts of things, are symmetric, bell-shaped, they are centered at 0. Yeah, so we're used to those things. But a chi-square test statistic is different. So the way it's calculated is for each little subgroup within a category, like for us, M&Ms have 6 colors, so we'd do this 6 times. We'd calculate what we count minus what the manufacturer said ought to be there, squared, divided by the expected. So we do that once for each of the 6 colors that we're going to handle, and then we add them up. Remember, this is your summation symbol, so we'll add them up from 1 to n is 6, and that'll produce your chi-square number. And then we have tables in chi-square CDF and inverse chi-square that we can use to generate p-values or, you know, whatever we need to do. Now, if you think about it, what is the smallest that one of these could ever be? Well, if observed and expected are equal, you know, if there's no difference between what we count and what the manufacturer says ought to be there, then the smallest we can get for any of these chi-square portions would be 0. So the bottom line here is that your chi-square value can never be negative. It goes from 0 on up. So that's a big difference between what you would see with chi-square and what you would see with z-curves or t-curves. So what we end up with is it's a sum of weighted differences of observed and expected values, and the weighting is going to be taking into account the magnitude of the differences. So imagine that, you know, observed minus expected has a difference of 10. Just make that up. That's a more meaningful value than if observed is 20 and expected is 30, than if observed is 1,020 and expected is 1,030. Because think about it, 10 is half of 20 and 1/3 of 30. So it's a big portion of those 2 numbers, whereas here, you know, I don't know, 10 is about a little more than 10% of this number, and maybe a little tiny bit more than that for this number. So the magnitude of 10 really matters more here than it does here. All right? So what do we have for chi-square density functions? Well, a density function, don't forget, is a mathematical model that's geometric and the area under it is 1. So we chop it up into probability. So at least that we have in common with our z-curves and t-curves. The domain, the value on your x-axis, is values at 0 or higher. All right, whereas we're negative to positive infinity for a z curve or a t curve. All right, none of your expected values can be 0. All your t curves are skewed to, chi-square curves are skewed to the right. Here are some of them, and they're based on degrees of freedom. Degrees of freedom are n minus 1, where n is the number of categories. So if we have 6 different colors in a bag of M&Ms, those are 6 categories, with the overall categorical variable being color. So n minus 1 is 5, right? So here we would have 2 categories, so 1 degree of freedom, and it's about as skewed to the right as it can possibly be. 5 degrees of freedom would be like 6 categories, and it's skewed to the right. All right, 10 degrees of freedom would be 11 categories, and it's getting a little bit more symmetric. Right? Doesn't matter how many categories you have, it'll always be skewed to the right, either extremely or less so. So your shape does depend on the degrees of freedom, and that's how you calculate them. And as the degrees of freedoms increase, your chi-square distribution becomes more symmetric. Now it says here approaches normal. Scratch that off, because look, your chi-square distributions start at 0 on up. They're always skewed to the right. They're nothing like a normal curve or a t curve. So it doesn't approach normal, it just gets more and more symmetric. Now the good news for us is that our tests are always one-sided. They're going to be from some chi-square number to infinity. We also do not have to deal with confidence intervals. So jot that down, no confidence intervals. The thing is if you have 6 categories, your HA will be so multidimensional in what's bigger than what or what's different from what, that there's no way that you can do a confidence interval. You know, with a 1 proportion z-test, yeah, you can get a confidence interval for the estimate of a true population parameter. For a 2 proportion confidence interval, you're just looking for 0 in there. But if you start with 3 or 4 or 5 or 6 proportions, there are just too many comparisons for it to fit in a confidence interval. So thus we don't have to do it. So that's great. All right, so scooting to the next page. We're going to start with a chi-square goodness of fit, 1 population, 1 characteristic. If we're only going to show 1 population, then we have no interaction with anything else, no other categorical variables. So this is sort of one-dimensional. And the nice thing is that hypotheses will be written in words, not symbols. I have them down here. We'll get to that. Now for assumptions, they've been updated over the summer. So we're looking for randomness. We have to add in the 10% rule. Population is at least 10 times the sample size. So pause if you need to jot that down. And all of our expected counts have to be at least 5. Now if you make a mistake and put 10 there, fine. You know, anything that's 5 or more will also be 10 or more. So you're going to be great there. We don't have to do independence. In fact, they talked about independence in the College Board materials that I have, and they said if your sample is random, that shows independence. Like, okay, fine, whatever. But I'm not writing it. The name of the test is the chi-square goodness of fit test, and we're going to have observed values in a table. That's required. Expected values in a table, along with every single observed minus expected squared over expected for each category. We're going to do these a number of ways with lists, and we're going to do them, you know, just from the test. I'll show you how to get these 6 values for our little activity today. And then we state the chi-square value. You can figure out the p-value by doing chi-square CDF from whatever your chi-square number is to infinity with degrees of freedom. That's certainly there. You can use it, but we will be doing a chi-square goodness of fit test to get that p-value. And then we're going to, you know, compare to an alpha or just, you know, judge on the strength of evidence, how big or small your p-value is, and follow and do a statement of conclusion and follow-up. So The M&M's activity. This is what we did. I put M&M's in 6 cups. We formed 6 groups. The groups counted up the colors and we put them in here. All right. And this is a spreadsheet that gave us all of the totals of the colors along with the total for n. We need that in order to get the expecteds. Okay. So we put these numbers here in the white in our table. So here's the table and here's the numbers. This was the first period data. It kind of varied throughout the day, but we ended up with pretty much the same outcomes. All right, so let's start out. HO, is it the proportion of colors of M&Ms or what the manufacturer claims? And I put those percentages down here. They're actually stated in the prior part of your packet, and that's what we went with. Now, HA is the proportion of colors of M&Ms are different from what the manufacturer claims. So, pause if you need to write that. All right, the assumptions. I did buy 2 bags of the big varieties. I forget how many ounces they were, but the whole total was like $16, so there was a lot of M&Ms. And we asked, is that going to be reasonably random? If I just grab a bag with a ton of M&Ms in it off the shelf and split them up into 6 cups, is that sufficiently random? And it kind of is, right? It's just that bag is just as random as any other bag. So yeah, so the sample was reasonably random. The population is at least 10 times the sample size. So I think we can go along with that. There's a lot of M&Ms out there. And then I did the expected counts, and you kind of have to save this until you figure out this part of your table. What I did to do it was I took all of my percentages and took them as decimals, like 0.13, 0.14, 0.13, 0.2, and so on, and multiplied those each to 607 to get my expecteds. Now, you're allowed to do decimals because it's like an average, right? So 607 times 0.13 gave me 78.91. And that's the same for red. And then 607 times 0.14 gave me 84.98, and so on. So I figured those all out. These are close. These are kind of close. This is close. Yeah, we're starting to really separate out with these 3 colors. All right. So we did a chi-square goodness of fit test. And let's go and consult the calculator to see what we got there. All right. So go ahead and, you've got that table filled in, hopefully. I called the first column O for observed, and here are the ones that I observed, right? All those are from the table. And the expected, I just typed those in too. All right, now the third part of our table is the, where'd it go? Is the observed minus expected squared over expected. So here's what we do for the calculator. All right, pause if you need to put that in. All right, I'll assume that you did put that in. We're going to scoot over and we'll go up here, and I named this thing X like it was chi, the Greek letter chi, and I threw in a formula. Right, so hit equals, and the first thing that needs to go in there is a fraction. That's control divide. So control divide, and you only see the numerator part. The denominator part's there, you just don't see it. So throw in some parentheses, and we'll type in 0 for observed, or not 0, but O for observed minus E for expected. All right, go outside of your parentheses and hit your X squared key. And then arrow down, and that's the denominator field, and we just need expected. So once you have that in, hit enter, and it's all that column reference, variable reference stuff. So right arrow and go down to variable, and hit enter, and tab to OK. It's going to ask you again. All right, so great. All variable references. Probably I should have asked that in the first place. And then tab to OK. And there are all those numbers that you need for this row here. So take a little bit of time to copy those down. And it's like 3 or 4 decimal places. It's not that big a deal. We're just going to use what we get in the calculator anyway. We just need that for comparison. So all of those go in. And so pause if you need to. And now we're just going to get out of here and we're going to run this test. So hit, what's that? On, I guess, and then go to a calculator page. And we want these two things linked. So from here, we're going to run the test. So menu, 6 for statistics, and then 7 for stat tests. And see right here, this chi-square goodness of fit test right there. That's exactly what we want. The two-way test will be for homogeneity and for independence, so we don't want that. Not yet. Okay, observe list is O. See why I named it that? Oops, not X, it's O. And the expected list, tab over to it, and that'll be E. And we have 6 categories. Remember, it's n-1, so we want 5 degrees of freedom. You got to get that right. So tab to OK. All right. There's your chi-square number, and there's your p-value. We just went ahead and called that 0 because times 10 to the negative 19, sure. All right, this is way different from 0. The closer you are to 0, the more alike observed and expected are. This is not near 0, okay? All right, so let's copy this down. See that? All right, so here's your chi-square number. P is about 0, 5 degrees of freedom, and we picked an alpha value, just to make it more comfortable. So since P is less than alpha, your results are significant, and we reject HO. So there is sufficient evidence to believe that the proportion of colors of M&Ms is different from what the manufacturer claims. Now I want to just pause right here and show you another way to get these little pieces of your chi-square statistic, because all of these 6 things add up to this, all right? So we need to figure out how to get them. We did see it from, you know, being in the table, like right here, but there's even a better way to do it. Because see up here in your results where it says comp list, the comp list is where all of those little pieces of your chi-square number are. And they're very accessible, right? All you've got to do, get a blinker down here and go to variables. It's right above 9. And you see where it says here stat comp list? That's what we want. So click on that. See, it's all bold. That means that something is stored there. Hit enter. And there are all of those numbers. Now what you probably need to do is arrow up and copy them. And they give you an ungodly number of decimal places. I don't know what that's all about. But once you have it copied, you can go in here and just left arrow, and just get all those numbers. And just jot them down without all the decimals, like what, 3 or 4 we said. So that's another way to get it if you don't really want to mess with that formula in a spreadsheet. They're all here listed under stat comp list under var. Okay? So there's that. So back to what we were doing here. Okay, so we rejected HO and we said that, yeah, these proportions seem to differ from what the advertiser or the manufacturer advertises them to be. So I think to walk away from this at this point would be to leave your reader kind of wondering, like they want more. So what we need to do is just go back into our table and find the 2 or 3 biggest discrepancies, because all these numbers are discrepancies. The biggest is green. If you look close, there's way more than expected. And if you look at your blue and your orange, there actually is less than expected. So I said that. So you ought to comment on the top 2 or 3. I said there is more green than expected and less orange and blue than expected. And that will give your reader a good sense for, you know, just exactly what is causing you to reject HO and say that these things don't match up. Where don't they match up? It's in the green, the orange, and the blue for the most part. Yes, all the other ones have discrepancy too, But we don't want to get too carried away. The top 2 or 3 biggest ones are where you list for your follow-up. If you are failing to reject HO, there is no need for a follow-up. You don't need to add that last little piece in there. And of course, if you have a violation of assumptions, you can throw those in there as well. All right? So there is a chi-square goodness of fit test. Seems doable, I hope. Another thing I wanted to show you, and I did show the others, was that in your packet you do have a chi-square table. See it? And it's sort of similar in a way to your T-star or Z-star table. You would locate your degree of freedom in your test and come over here. These are all chi-square numbers, and you're probably not going to find yours, but you will find the values to either side. You can read up and say, my p-value is between these 2 numbers. It's less than alpha. I can reject HO. Trust me, we never use these. Never. They're on the back of the charts that were available to you for proportions and means, so you're welcome to them. But really, a TCDF will be way more accurate just from your, TCDF, I mean chi-square CDF. From your chi-square number to infinity with your degrees of freedom ought to be perfect. And you even have an inverse chi-square stuffed away in your calculator. In fact, just for grins, let's go ahead and do one. All right, probability distributions, chi-square CDF. All right, the lower bound, let's go with 98.032. And the upper bound was 1,000. And we had 5 degrees of freedom. All right, don't let me down. All right, there we go. It's a little off. I probably typed in some of the decimal parts wrong, but you get the idea. If I'd put this number in right, it would have come up to the exact same p-value that I had. All right? All right, that is what we learned.